In the series, we're looking at the wonderful world of bounding volume hierarchies, enabling real-time ray tracing on GPUs. And we've got the list of verticals. This is the third one. And we're talking about how to reduce the time it takes to build a good BVH. This will be important for the ultimate goal of building a BVH for a large-scale dynamic environment, which is the topic of a later article. The previous article, the surface area heuristic was introduced to improve the quality of the BVH. Using creating a high-quality trees, one that can be used to quickly find the intersection between array and the scene. Surface area heuristic works wonders, and when it's combined with ordered traversal, the naive BVH from the first article is outperformed by a factor of 3. There's a catch, though. Building with the surface area heuristic it takes multiple seconds, where the basic one takes milliseconds. And that's on a fairly simple mesh still. I actually tried this a little bit on like a Sponza mesh, and it was, depending on the situation, you could have it take like 40 minutes. It was kind of ridiculous. But then tracing it is not expensive. Anyway, so the reason it's simple: for n polygons, we have to evaluate n split plane candidates on each axis. So the split plane evaluation involves basically touching every primitive in the list there. So algorithmic complexity is n squared for one split. So it's not great if we hope to build BVHs for much larger scenes, and also not something we can solve with parallel code or just basic optimization here. So for new concepts introduced in this article, we need to clean up the subdivide function somewhat. Splitting of the code defined. So we've got start splitting of the code defines the optimal split plane position and access to a function. Find best split plane. Simplifies the relevance section to in subdivide to this, and so what this is doing is so through the 3 axes, we've got some number of triangles, and then we're evaluating centroids, and then the surface area heuristic is the expensive part. Jesus. So using that in subdivide, it's just a function call there. So it checks to see if the best split cost is actually an improvement over not splitting. So we can make that a bit more clear. Using a function that calculates the cost of an unsplit node. Like that. So we're looking at surface area there. I guess, yeah. Okay. Back in subdivide, we call calculate node cost after finding the best split plane and terminate if it isn't worth it. Okay. So okay. So you're evaluating whether you want to make a split or not, and that's if it's worth it. If it is an improvement to make the split, then you do it. If you don't, you don't. So. Straightforward way to reduce the time complexity from n squared to n is to use the midpoint algorithm. However, we have very good reasons for not using that because it produces a rather poor tree to evaluate against. What would happen if we did not just consider one position but several or many? Intuitively, there shouldn't be much of a difference between these two situations. Where on the left we have split plane candidates that are through the centroids, and on the right we have uniformly spaced split plane candidates. In fact, if we use a high enough number of uniformly spaced planes, the solution should converge to the same number as the full SAH sweep. So we start experimenting. At which number of planes do we still get a reasonable tree? Okay, so it's for the three axes we're looking at. Okay, yeah, the bounds thing there, and then so for 100 subdivisions, we're looking at a candidate position that is the axis position, the minimum axis, evenly spaced between the minimum axis position and the maximum. Then evaluating the subtree there. Okay, yeah, for that axis with that position, and seeing if it's lower than the best cost, which is yeah, okay, that's just initially a large number. Okay. So, number of intervals, we're separating by 99 planes, which will be the split plane candidates. So that's instead of iterating through all the triangles in the subtree, I guess, is what we're looking at doing. So, okay. Planes are fixed distance apart to prevent any repeated division by 100. You just pre-compute that. Offset. Running the code gets us our first results. Building it is much faster because 100 is much smaller than the n triangles. I'm taking 350 milliseconds and evaluates in a reasonable amount of time as well. It turns out the smaller number of planes just gets us a pretty decent tree. At only 16 planes, rendering takes 110 milliseconds, but the build is much faster at 60 milliseconds. At just 8 planes, we're still getting something pretty reasonable, and it builds even faster. So even going to 4, it's still pretty reasonable. Interesting. So you can now you have a trade-off. You have some knobs there for balancing quality and speed. This is useful, especially once we start rendering animated scenes. A model that occupies just a few pixels and changes every frame justifies a very quick and dirty tree. Your build time is your more important stuff, and then full screen static scenery should use a tree that is high quality no matter the costs, because you're going to be evaluating against it so many times. We can control this now, especially when we realize that we left one trick unused, limiting the surface area heuristic sweep to the longest axis like we did with the midpoint split. This comes at a minor degradation of tree quality, but it builds even faster than that. So limiting the SH to the longest axis. Okay, so that's just doing, instead of iterating through the axes, it's just going to pick the longest one and do it. Okay, so let's get some options there. So tweaking this, we got the initial code for the uniformly spaced planes. I assume that we should subdivide the full extent of the axis-aligned bounding box of a node. This is not strictly necessary. Strictly not necessary. In the SAH sweep, first split plane candidate is the first centroid. The last one on the last centroid. Better range of values is to cut up. Is thus the AABB over the centroids of the primitives. Turns out that this matters. Better range of values to cut up. AABB over the centroids of the primitives.
Just look at the below image.
Yeah, I guess, yeah. So we're building another AABB that's just the vertices, or just rather the centroids, rather than containing all the primitives, I Okay, so bounds over the primitives versus bounds over the primitive centroids. So we're looking at the blue box becoming the yellow box. We shrink that down to just the centroids. Centroid bounds are quickly found using the loop over the primitives. And then that replaces the two lines that read bounds min and bounds max directly from the node bounding box. At 4 and 8 planes per dimension, this slightly improves the resulting tree. Minimal cost. So binning the Unity vehicle mesh that I provided in the last one was about 12,000 triangles. Using fixed planes now builds in milliseconds, but it turns out that we can do much better than we had done so far. So we're looking at a diagram with evenly spaced planes. Here we've got 7 planes separating 8 intervals. Each of the primitive centroids projects to one of these intervals. We can now calculate the bounds of each interval and the primitive count for each interval. Once we have this data for each interval, we can efficiently determine the union of the bounds of a range of intervals, as well as the sum of the primitive counts of a range of intervals. And this in turn is exactly what we need to evaluate the SAH, this time without visiting every primitive multiple times. Interesting. So we're looking at bounding boxes for the primitives that fall into these intervals in particular. So it's a bounding box for the ones that are contained in that interval. Okay, so for making a list of bins, each one has a bounding box and a count of primitives. Populating the bins by visiting primitives once per axis. So this outer loop is going to be by A. Bins is the number of intervals, yeah. So we divide the range by a number, or whatever. So then we put all the triangles into these bins. Okay. The bin index for a primitive centroid is calculated as the centroid minus the minimum bounds times 8 over the bounds maximum. Okay, so it's just a remap there from bounds min to bounds max to 0 to max, basically. So once to prevent the division per primitive variable scale stores the non-varying part of this equation. Once we've determined bounds and primitive counts for the bins, we can use this information to calculate the info that we need for each plane. Our final goal is to evaluate the surface area heuristic at each plane. For this, we need the following information. We need to know how many primitives are to the left and to the right of the plane. Bounding box over the primitives to the left and the bounding box of the primitives over the right, or to the right. We need this data per plane, so we store this in some other arrays. We can fill these arrays with a sweep over the bins. We do a sweep from left to right, populate the left area and left count arrays, and then a sweep from right to left to populate the right area and right count arrays. So we have everything in bins, and then we are iterating through and the bins, and then we say left sum plus bin dot try count. Note that the sweep from left to right and from right to left happens simultaneously. The left box starts as an empty array, or an empty AABB, and each bin is extended with the bounds of that bin. Okay, so it's becoming larger as you progress. Likewise, left sum used for the summed triangle count starts at 0 and increases with the bin, or the counts stored for each bin. Variables for the right side are updated in the same manner, but starting from the end of the array and coming down. That's interesting. After the arrays have been filled, we can evaluate the surface area heuristic for each plane by looking at these arrays. And then once again, scale is used to prevent the division. The full subdivide function is now somewhat larger and has all the pieces we just looked at. So it's first we're looking at, well, over the 3 axes, we are initializing best cost with a large number. We say for the 3 axes, we've got some number of triangles in this node. We're going to evaluate minimum and maximum of the bounding box just for the centroids, not for the entire primitive. If bounds min equals bounds max, then that's a degenerate node. Doesn't have any contents. Or, well, I guess it would just be one, wouldn't it? Potentially, yeah, just one primitive in there, and then or primitives with the same centroid, I guess, more accurately. Populating bins, and then gathering data for the 7 planes between the 8 bins, and then the surface area heuristic cost for each plane. And then updating the best cost with the cost for each plane if it is less than the current best cost. So using 8 bins on the BVH now builds in 11 milliseconds, 3 times faster than before. Didn't time the yoke. This is without any SIMD or low-level optimization. So next, now that we can build the BVH this rapidly, we're ready to consider animated scenes. Before we go there, 2 more ingredients are needed. We need to refitting and rigid motion for BVHs using ray transforms. Okay, interesting. They combined with fast rebuilds, these ingredients unlock the full potential of the top-level BVH, which will finally let us ray trace massive scenes with large moving objects in real time, even on the CPU. But that's material for another day. Complete project is available on GitHub.